So what we are going to start chapter 5 of the book. Chapter 5, electrodynamics of continuous media. Okay. So the topic is ferromagnetism. Ferromagnetism आपको पता है as a property. You might know that in presence of a magnetic field, the magnetic those they get aligned. Now there is a subtle difference. For example, there are some properties. So before we are going to say something about ferromagnetism, we should also have some idea of something called ferroelectrics and so ferromagnetism ये है कि one is a magnetic property, one is the property by virtue of charge, है ना? So they may not necessarily be the same. So अगर किसी भी कंडक्टर में whether it's magnetic property or whether it's electric property, these are two properties, and those properties may be interact with molecules, atoms, electrons, spins, but they will have different how they are going to interface if externally we are going to apply some E field or a B field. Okay, so they will have two different interactions. They will have two different effects. So in the first domain, so what the notion of ferroelectricity is that you might have studied polarizability as a phenomenon. उसमें polarizability है ना, as a tensor, as a quantity. So charge की जो ये है orientation है, it depends upon इधर से है, उधर से है, ऊपर से है, नीचे से है ना? And relatively जो magnetic field है ना, magnetic field is aligned in a certain preferential direction, है ना? B field. So जो B field है normally when we talk of ferroelectricity, so the properties of magnetic field which in turn may be normally associated with the magnetic dipole moment जो spin के साथ हम associate करते हैं, ठीक है? तो उसमें थोड़ा सा उतना पोलराइजेबिलिटी नहीं होगा जितना इसमें ये वाली प्रॉपर्टीज में, ठीक है? अब फंडामेंटल लेवल पे when we have a microscopic understanding of matter, microscopic understanding of what are the quantities which will differentiate this thing from this thing. अब इस चीज को हम करते हैं, we are going to our study of phase transition, study of phase transition at critical point, at या इसको आप sometimes if you have studied in literature Curie temperature सुना है ना? Curie temperature is the temperature at which the magnetic it loses magnetic property. So what we are going to study is ये जो दो phenomena है ferroelectricity and ferromagnetism को we are going to study it from our understanding of second order phase transition. सेकेंड ऑर्डर फेज ट्रांजिशन पे एक क्रिटिकल पॉइंट आता है, ठीक है? क्रिटिकल पॉइंट पे हाउ डू द मैग्नेटिक प्रॉपर्टीज अबोव एंड बिलो क्रिटिकल पॉइंट, अबोव एंड बिलो दैट क्रिटिकल पॉइंट जो होंगी, देयर कम सम subtler differences, ठीक है? Once we study phase transitions above and below critical point, ठीक है? So there comes some when we analyze it, there comes some differences. उससे हमको वो चीजें when we just study in some detail, that will give us how we can differentiate a substance as ferroelectric or ferromagnetic. ऊपर से ferroelectric की में ये प्रॉपर्टी है कि वहाँ preferential direction नहीं होती. इस तरह you can have a field can be any. It depends upon polarizability molecules की कहाँ होगी. इधर होगी whichever direction you are. While in case of magnetic field, due to magnetic dipole moment, उसका थोड़ा सा एक प्रेफरेंशियल एक अरेंजमेंट हो जाता है. बट डीप डाउन जब हम मैटर को स्टडी करते हैं, सो whether it's ferromagnetism or whether it's ferroelectricity, so these properties, how we can have a minor classification. So we are going to take our understanding of phase transitions or second order phase transitions, and the phase transitions happens at some critical point, उसी को हम कहते हैं Curie point in your solid state physics you might have studied. अब इसमें ये है कि we are not going to study phase transitions. Phase transitions you might have, जिसका पिछली क्लास में हमने कहा था Clapeyron classes Clapeyron equation जो है, how you study phase transitions. एक फॉर्म वही है, solid goes to liquid, liquid goes to gas, gas goes to. So you can take here the phase transition is that domain walls अगर होंगे, they are preferentially एक direction में है, ठीक है. At some temperature the domain walls का जो है ना state, it gets disturbed, उसका phase transition आ जाता है. अब this entire thing इसका हम एक thermodynamic treatment लेते हैं. जिस तरह हमने मिस्टर इफेक्ट और अदर इफेक्ट्स को लिया ना, when the magnetic field is strong, the superconducting state of a it doesn't become superconducting. फिर हम कहते हैं कि intrinsic properties of the system, जैसे टेम्परेचर है, वॉल्यूम है, ठीक है, प्रेशर है, वो when the magnetization, when the superconducting से normal conducting होता है, temperature increase or decrease होता है. So there are some parameters intrinsic to the conductor, ठीक है, without reference to external things, which will describe whether ये system superconducting रहता है कि नहीं रहता. So in the same way there are some parameters intrinsic to that material at that point of criticality. Those parameters, whether it changes with temperature, whether it changes with pressure या उसकी entropy, ये सब हम calculate करेंगे. So this is our class, the broad outline of the class, ठीक है. अब इसमें ये है, the thing is that for example notion of spontaneous polarization है ना, एकदम से spontaneous polarization एकदम से you will apply something. For example आयरन के है ना, आयरन फिल्म्स आप रखोगे एक जगह, यहाँ मैग्नेट हो एकदम से हो जाता है इस डायरेक्शन, है ना. अब ये spontaneous polarization जो है, whether it's due to ferromagnetism or it's this अब इसमें ये है कि जो मैग्नेटाइजेशन एज अ फिनोमेना है ना, उसमें इलेक्ट्रॉन्स और मैग्नेटिक मूवमेंट ऐसे स्मॉल टाइनी करंट्स आर देयर, बट उनकी जो वेलोसिटी है ना इलेक्ट्रॉन्स की, दैट्स रिलेटिवली v स्क्वायर बाय c स्क्वायर, है ना, at very larger velocities. So we can at that thing we say there are एक होगी normal interaction, दूसरा होगी exchange interactions. तो exchange interactions होगी जो dipole जो normal neighboring atoms neighboring molecules में interaction हो जाती है, और एक इंटरेक्शन होगी when the particles are moving at very, उनका अपना एक फील्ड एसोसिएट. हम ये मान लेते हैं कि that this exchange interaction is very greater than when the particles are moving at very higher velocities. So magnetization of a ferromagnetic quantity is a first order approximation. On the basis of exchange interaction is conserved. अब हम क्या काम करेंगे, जो मैग्नेटाइजेशन है ना एज ए फिनोमेना एम, वी विल डिनोट इट बाय एज एम. एम is required as an independent variable. And इसका जो एक्चुअल वैल्यू लेंगे विल टेक एट सम थर्मोडायनेमिक इक्विलिब्रियम. जिस तरह हमने कहा था ना उस टाइम, बाहर से मैग्नेटिक फील्ड इंटेंस होगा, अंदर में थर्मोडायनेमिक टेम्परेचर चेंज हो जाएगा. बट हम लेंगे एट सम मीन थर्मोडायनेमिक इक्विलिब्रियम. ठीक है. सो उसमें हम मैग्नेटाइजेशन को हम लेंगे एज एन इंडिपेंडेंट वेरिएबल. इट्स नॉट चेंजिंग, इट्स नॉट, बट सम एट इक्विलिब्रियम स्टेट, not at a non-equilibrium state. So we are taking some approximation in our model. So equilibrium state पे हम magnetization को as independent parameter नहीं लेंगे. So to begin with, so in order to find the thermodynamic potential per unit, so यहाँ तक तो ठीक है, that's fine. And we are also going to neglect the relativistic interaction. अगर अब ये दो चीजें हमने ले ली तो हम ये कह सकते हैं कि now we can say it like that. तो we know that d phi by dh जो है, you might be knowing this equation where it's also equivalent to h plus 4 pi m. The flux, change in flux, you can see it's equal to magnetization, and this is this. इसमें h में है mu naught, ये magnetization है. So ये equation you are knowing. Now what we are going to do is we are going to have integrate for a given value of इंडिपेंडेंट वेरिएबल. इंडिपेंडेंट वेरिएबल ये है कि ये मैग्नेटाइजेशन जो है, we denote it as magnetization as an independent variable such that phi naught is equal to phi naught 0 m minus m dot h minus h square by 8 pi. h square by 8 pi, if you remember, ये हमने कल भी कहा था, it's the internal magnetic energy of the system at rest of जो भी है. इस तरह टोटल इलेक्ट्रोस्टैटिक एनर्जी है, इस तरह टोटल मैग्नेटोस्टैटिक एनर्जी भी है, उसका वैल्यू ये आता है. ये मैग्नेटाइजेशन है m डॉट h, ये फाई नॉट है. सो व्हाट वी आर गोइंग टू डू, we'll write it as equation 3.6.1. अब इसको थोड़ा सा अगर हम इंटीग्रेट करेंगे ना यहाँ से, इंटीग्रेट इफ वी विल डू, सॉरी, we are going to integrate this function. अगर आप इसको यहाँ लाएंगे ना, ये आएगा h dh plus 4 pi m dh. ये भी 4 pi है, ये भी 4 pi है, तो ये h dh आएगा h square by 2, h square by 8 pi, यहाँ से भी आएगा, सॉरी, h square by 8 pi आएगा, ये m dot h आएगा, ये है ना dh का इंटीग्रेशन, इसका इंटीग्रेशन ये एम एच आएगा, ये एच स्क्वायर बाई 2 आएगा, ये 8 पाई आएगा. सो मे बी आई यहाँ से आएगा, एंड दिस इज इंटीग्रेशन कांस्टेंट, है ना. ये फाई को आप इंटीग्रेट करोगे ना, 5 माइनस 5 0, सो ये 5 0 आएगा. सॉरी, ये मैंने, इट्स नॉट ड्यू टू दिस, इट्स ड्यू टू दिस. सो वी इंटीग्रेट this equation, इस equation को integrate करके we arrive at this equation. Once we arrive at this equation, and we will have some hence the potential phi. So इसको थोड़ा सा हम इसको in terms of h dot b by 4h, we are going to थोड़ा सा इसको करेंगे, we are going to rearrange, it will be equal to 4 pi m square by 8 pi. rearrange कैसे करेंगे? So b चलो यहाँ तक ठीक है ना. So this is fine. 5 plus 5 h dot b is equal to 5 plus you just wait for something. So we have done nothing. We have just I would did the idea. We are rearranging this equation. Rearranging this equation in terms of m and b. So we'll get this. If we are not able to come, you just wait it for some time. So if we can write 5 like this, then what is the next set of things we are going to do? So we can replace, for example, we have magnetic anisotropy of ferromagnetic. अगर magnetic anisotropy है ना, एक होगी isotropy. Isotropy means things are having इस direction में component होगा, इस direction में. Anisotropy means the components are having different. So if you can neglect anisotropy, we can say that जो this 36.1 इस इक्वेशन में और इस इक्वेशन में जो हमारी जो है डायरेक्शन ऑफ वेक्टर्स may not be that important. Direction of vectors of m and h, है ना, it may not necessarily be important. We can only take it as a magnitude ही ले सकते हैं. That will suffice for us. अब हम आएंगे क्यूरी पॉइंट में. सो नियर क्यूरी पॉइंट we are going to use theory of second order phase transitions. ये पढ़ा है आपने, second order phase transition पढ़ा है? So if you have studied, you just थोड़ा सा इसको rehash करो. And so what we are going to do, I am straight away going to write the second order phase transition पे equation क्या है. We will only have some even poles. So जो phi है, जो for example expansion of isotropic function as powers of a vector quantity m. phi का हम वैल्यू लेंगे ऐसे 500 plus 1/2 am square bm4 minus mh minus h square by a, where 500 a b are functions of temperature and pressure. So now we are getting thermodynamic quantities जो मैं कह रहा था. तो उस सिस्टम में at that phase transition जो हमारे पास है, so we are taking, so this is the general phase transition पे क्या equation है second order phase. अब यहाँ पर हम क्या करेंगे, this quantity A and this quantity B, it depends on, it's a function of temperature and pressure. And such that at Curie temperature T is equal to 0 is given by vanishing coefficient of A. अब इसमें Curie temperature above 0 और below 0, उन दो conditions में for A greater than 0, for T greater than 0, and for A less than 0, T is less than 0. अब at जो Curie temperature है ना ये A, so we'll expand it near Curie point, near that transition point, जहाँ पर इस तरह transition point क्या है, Clapeyron equation में transition point क्या है, solid change to liquid, gas change to vapor, ऐसा कुछ. So यहाँ transition point है कि Curie point, where the substance loses the property of magnetization. या domain walls का जो preferential alignment है, that's disturbed. तो that depends upon some temperature. एंड दैट हमने ए को इन टर्म्स ऑफ टी लिखा, सो उसमें 2 पॉइंट्स आएंगे, एट बिलो, एट so at temperature below it will have the property of magnetization, at temperature above it will lose that temperature. So so it will be d minus theta. So A can be written as, so we'll write it A in terms of t minus theta. Okay, A is in terms of t minus theta. Theta can be plus or minus. Or so we can write a quantity which depends upon temperature. We can also write it A as alpha into t minus theta, and alpha can be positive quantity independent of temperature. एंड द कोएफिशिएंट जो b है इसका वैल्यू हम लेंगे उसी वक्त जो उसका वैल्यू होगा एट दैट पॉइंट. अब हमारा काम है now what we are going to do, see what we are going to do. So we are going to see d phi, जो मैग्नेटाइजेशन हमने लिखा ना एज अ कांस्टेंट फॉर अ गिवन वॉल्यूम एंड प्रेशर. Now we are going to change this phi in terms of m. It will come out to be, अब ये है ना a को in terms of आप देखो a in terms of alpha into t minus theta m square. So now the equation has changed. So you can write it in terms of alpha t minus so you will differentiate with m. ये तो आएगा twice m, ये आएगा 4m cube, ये आएगा खाली m. So we are going to neglect some higher quantities and write it in terms of, so ये m है ना अपना twice m, 2 कट जाएगा, m बाहर निकला, a के बदले अल्फा माइनस टी माइनस थीटा रखा, ये 4m क्यूब आएगा, तो m क्यूब ये है, ठीक है, 4 इसके साथ कट जाएगा. So you have first order where phi is the minimum. अब जिस तरह आप कर लेते हैं कोई भी सैडल पॉइंट मैक्सिमम या मिनिमा निकालते हैं. So we are going to have at this point transition point एक less than 0, एक greater than 0. So where this is transition point where phase transition happens, और Curie point जहाँ होता है. तो जो ये m है, phi is the minimum. Then expression in the brackets is 0, है ना? Minimum तब ये आएगा ना, even this d phi by dm is 0. And m का वैल्यू क्या आएगा? So if it is 0, so m का वैल्यू आएगा शाबाश. So m, so it will also be 0. ये m square आएगा, m ये आएगा minus alpha t, तो it will also be equal to alpha theta minus t by b. It's 26.5. So at that transition temperature, if it is 0, okay, m का वैल्यू दिया है, so if it's 36.5. So thus as we approach the Curie point, spontaneous magnetization पे हम पहुंचे, ठीक है. So this is the part. The spontaneous magnetization अब यहाँ the spontaneous magnetization decreases as theta minus t, है ना, यहाँ पर m theta minus t है ना, ये t decreases like that. आप देखो ये it decreases as आगे इसका कम वैल्यू हो जाएगा ना यहाँ पर for different values of t. 1 तो ये कम आएगा, दूसरा वाला उससे कम आएगा. So that's what we say. It decreases as spontaneous magnetization decreases as theta minus t. Like any second order phase transition at Curie point, h is equal to 0 is accompanied by discontinuity in specific heat. है ना? किसी भी फेज ट्रांजिशन का एक प्रॉपर्टी होती है, देयर इज डिसकंटिन्यूटी इन स्पेसिफिक हीट. ठीक है, मेजर स्पेसिफिक हीट एट फेज ट्रांजिशन. तभी तो आता है ना ऐसे फंक्शन इज स्मूथ एंड सडनली इट बिकम्स ठीक आता है कुछ. ठीक है, so if we neglect higher powers of m. now पहले हमने किया d phi by dm as a magnetization. magnetization is constant. अब इस phi को हम करेंगे in terms of temperature. that will give us entropy, and we are going to not take these higher powers of this m. we are going to take as 0 m square dA by ये है ना m square अपना dA by dt. ये f00 के बदले आपने कहा as an entropy, as a quantity है ना, d phi by dt. so f00. so we are neglecting the higher orders जो भी हमारे पास आ रहे हैं. so in the non ferromagnetic phase, m is 0 and s is equal to 0. While in case of ferromagnetic phase, m is given by 36.5. m is given by 36.5. ठीक. so that s, अब s को in terms of हम m लिखेंगे. we are going to substitute m का वैल्यू यहाँ पर. so it will be S00 प्लस m स्क्वायर के बदले आप लिखो ये आएगा अल्फा इंटू थीटा माइनस 2 जो अल्फा स्क्वायर t माइनस थीटा बाय 2. अब चेंज इन स्पेसिफिक हीट क्या आएगा? चेंज इन स्पेसिफिक हीट आएगा ds बाय स्पेसिफिक हीट ये. तो नाउ वी आर गोइंग टू डू दिस. सो इट विल कम आउट टू बी, so it will be constant. the first term will be 0 and it will be alpha square theta by 2. so this equation is 36.6. Now what? Now so the argument of the if you study the section, so the argument goes like this. So if let h is not equivalent to 0 and the condition d phi by dm is equivalent to 0, which determines the magnetization becomes. So magnetization की condition जो है, if we have this h is not equal to 0 and change of d phi by dm is equal to 0, so जो इस equation का form जो हमारे पास आएगा, it will come out to be h. आएगा कि नहीं? चलो from 36.4 36.4 is this is 36.4. so from 36.4, if d phi by dm is 0, चलो ये ठीक है, and h is not equal to 0, so this equation will have this form. This equation will have this form. So you can see it. So for the particular condition जो हमारे पास magnetization की है, ठीक है, where ये 0 है and h is not equal to 0, so this equation जो है इसका form ये हमारे पास आएगा. And who defined magnetic susceptibility? अब हम अपनी बॉडी पे आएंगे. So normally in your earlier classes of you might have studied solid state physics, so you might have studied susceptibility, है ना? Magnetic susceptibility दो ही चीजें हैं ना, एक susceptibility है और एक polarizability. एक chi है, दूसरा m है ना? अब यहाँ in ferroelectrics and ferromagnetics, both phi and chi and m are involved. So हम in some limited controlled conditions of how we define this magnetization को हमने constant रखा in a given volume. So we are arriving at something. So chi का हम लेंगे. Now we are going to take chi क्या है, polarizability की susceptibility. Now we are going to susceptibility को हम ऐसे define करते हैं. This is 36.7. That's we have paramagnetism with susceptibility which is inversely proportional to T minus theta. Proportional to T minus theta. कैसे? Like Curie और West law की वजह से, है ना? देखो यहाँ पर d, if you again do dm by dh, ये आएगा ना, ये डिनोमिनेटर में आएगा यहाँ से, ठीक है? So you go to do it from this side. So you say, so it's inversely proportional to t minus theta by Curie law और West law, जो भी आप कहना चाहेंगे, ठीक है? Where m जो है ना, m है हमारे पास, और अगर यहाँ से आएगा बेटा थीटा माइनस टी बाई अल्फा, टी बाई बीटा. हाँ, यहाँ से भी आ सकते हैं. So when h is equal to 0, so we obtain when h is equal to 0, when h is equal to 0, we will obtain, when h is equal to 0, we will obtain chi is equal to 1 to alpha theta minus t. अब यहाँ पर एक starting point है. Starting point is this thing that it should be pointed out that this quantity is not susceptibility. ये quantity ये कह रहा है ये susceptibility नहीं है. In the ordinary sense of the word, ordinary sense of the word हो गए जैसे generally we define things. Generally हम susceptibility को ऐसे define करते हैं, m is proportional to h and n is not equal to 0 even when h is equal to 0. इसका मतलब क्या है? So normally susceptibility is proportional to h, but even though when m is not equal to 0, so here this is a minor point which comes from our this analysis जो भी हमारे पास आ रहा है, that we are able to have a definition of susceptibility not in the traditional sense जैसे आप पढ़ते आए. So even at some value of h which is equal to 0, n is not equal to 0. Magnetization का कुछ value होगा even though h may be equal to 0. So this you just on room it. या इसको थोड़ा सा गौर करेंगे. और इससे if I write the sentence of the book which will ये पॉइंट को थोड़ा हाईलाइट करेगा। वो कह रहा है कि मैग्नेटाइजेशन M changes only very slightly with magnetic field. And may be regarded as constant for any given temperature. इसका मतलब मैग्नेटाइजेशन M changes only very slightly with magnetic field. And may be regarded as constant. So slightly change हो जाता है magnetic field. Otherwise it will remain. So this is normal sense में it will remain constant throughout. But यहाँ थोड़ा सा slightly change हो जाता है. And this is the way जो slightly अगर हम ferromagnetism and ferroelectricity का differentiation यहाँ से पूछ सकते हैं. How we fundamentally define ferromagnetism depends upon your magnetic moment, and ferroelectricity depends on the exchange interaction और जो वहाँ पर है neighboring interactions of ions, atoms. So this property differentiates them at this point, at this temperature. ठीक है?